Let's do a little bit more of a traditional Poisson problem here. Consider a certain experiment. Okay, so if you've got a radioactive particle, then the number of particles it gives off in any 1 second can be measured. Okay, if we know from past experience that 192 particles are given off in 60 seconds or in a minute, then we can talk about certain probabilities of other things happening. Okay, so the situation is that you've got this molecule and it sends off alpha particles. How many it sends off? Well, usually it sends off 192 in 60 seconds. Okay, now that's not going to be always perfect. It'll be around that. So I've been given a rate of success, and that's usually what defines a Poisson probability. Okay, so here I'm going to do something called reparameterizing this distribution. Okay, originally I've got this rate 192 particles per minute, but here as you read the question, what's the probability that no more, so less than or equal to 10 particles, appear in the next 5 seconds? Here the issue is this question is asking about a time period of 5 seconds, and the rate we've been given is in terms of a minute. So we need to change these so that they're in the same context. Okay, so I'm going to change, instead of being out of minutes, I'm going to change to be out of 5 seconds. We expect 192 particles per minute. Okay, so that could be rewritten as 192 particles per 60 seconds. Here I'll just divide 192 by 60, which will give me particles per second. Okay, so that is about 3.2 particles per second. This is just a similar unit here, okay? But I don't want in terms of seconds, I want it in terms of 5 seconds. So I'm going to multiply this 3.2 by 5, and what I end up getting here is 3.2 times 5, which is 16 particles every 5 seconds. Okay, so here now these two are in still the same terms. Okay, so how many alpha particles do I expect in a 5-second period? I expect 16, and I'm going to find the probability that no more than 10 were actually released. So it's going back to the original idea. If I've got a radioactive particle and I expect it to emit 16 particles in 5 seconds, I'm going to find the probability that I actually get 10 or less. Okay, these are possibilities. Just because it emits particles doesn't mean it's always going to do it like clockwork. We want to see the probability that we actually get 10 or less, even though we expect 16. Okay, so let's define a random variable x to be the number of successes or particles in a 5-second period. X then is a Poisson, where its rate of success is 16 particles per 5 seconds. Again, I always want these units to be in the same same context as each other. Writing this out, the number of particles that could have been expressed by this molecule, anywhere from 0 all the way to infinity. Okay, so it's possible that it spit out an infinity amount. Well, not really, but some large number. Okay, so, or it could have spit out 0, 1, 2. Here in this question, we're being asked, what's the probability that no more than 10? Okay, so that's also could be written as less than or equal to 10. Okay, so if I was doing this by hand, I could do a probability of exactly 0 plus the probability of exactly 1 and all the way up to 10, then add them up. Or of course, I could use Minitab, seeing as I have the less than or equal to sign. Let me show you how to do that. Here I've got my lambda, or my average, for 5 seconds. What I'm going to do is go probability distribution, Poisson. In this case, I want a cumulative probability, so 0 all the way up to 10, where the average is, on average, every 5 seconds, I get 16, and I want less than or equal to 10. Okay, so the probability of that happening is about, close to 8% chance. Here you can see the actual number. The probability of getting 10 or less particles in the next 5 seconds is about 7.7%. Pretty rare, because we expected 16, so having less than 10 would be a little bit unexpected. Just how unexpected? Well, about 7% or about 8% of the time this would happen.